Hi class, we are now on chapter 5.4. We're going to be looking at a molecular view of elements and compounds. So here is a classification. We start with pure substances, and they can be broken down into elements and compounds. So let's look at elements first. Elements are what is on the periodic table. That's very simple. If it says element, look at the periodic table. That is a pure substance broken down more into elements. Now we have two different types. We have atomic and we have molecular. What is the difference? Molecular is atomic. However, it means more than one. Where atomic is one atom, molecular means more than one. And what happens, and it'll be discussed on the next slide, that some elements are found naturally, not as a lone atom or broken, it's naturally as two. So we call it diatomic. These are gases. Most of them are gases here. And oxygen is O2. It's found as O2. Hydrogen is found as H2. So this is where the term molecular comes from over atomic. Compounds, now this is where compounds are fixed ratios. We have molecular and we have ionic. Molecular is nonmetals joined together. H2O is a perfect example in a specific ratio. Ionic is sodium chloride. It is metal and a non-metal. I should say ionic is a metal and a non-metal joined together where there is a transfer of electrons. So there's charges that hold them together. Now, sodium chloride has many atoms, but we do not put them in the ratio as molecular because we call this a lattice structure. So we only count what is actually made up and not the subscripts of it because it forms differently where these are separate, but they can still be attached. Ionics tend to be in solid form and they are very in a discrete, organized structure. So we don't count all of these separate. We just look at it and say, okay, this is sodium chloride. We're not going to count it as Na2335, something like that. 23 sodiums and 35 chlorides and so forth, or even 235. That's too much. So we use simplistically for ionics, we do not do that. We just look at what it is and we say that ratio of that. Where molecular, because they can be separate entities and still be attached, we can say exactly this is 2 hydrogens and 1 oxygen. So those diatomic molecules, here they are, and you should definitely know them. They are nonmetals. Most of them are halogens. You can see this. So why is this going to matter? Because eventually we're going to have to start writing out balanced equations, writing out chemical reactions, and you have to know how these form because we're going to use calculations, and putting oxygen as 1 oxygen over 2, everything's going to be wrong. And that means that you've probably spent hours only to have everything wrong from the very first step. It happens. So let's try to avoid that by knowing these. This is something you definitely need to know. You need to know which ones, there's 7 of them, and you need to know how they are written. So atomic elements are single atoms, and that's how they are in nature as basic units. Most elements fall into this category. However, molecular elements do not exist like that. They exist as more than one unit. So we call them diatomic. That's 2 atoms, and there are 7 of them. Hydrogen, nitrogen, oxygen, fluorine, chlorine, bromine, and iodine, all nonmetals. Okay, so an atomic element is a basic unit that composes mercury. So if we get to an element and you pull away and keep going down into level, you will finally get to one single mercury atom. That is as far as you can go and still consider a mercury atom. If you go inside, yes, it's part of what determines that mercury atom, but those are subatomic particles and they don't have the same behavior as the single mercury atom. So that's what we call it, atomic and one. Even though it's not really, you're just breaking it away. A molecular element, however, is composes like, for instance, chlorine. It's a molecular. It's diatomic, so it's composed of 2. This is the difference. If you break down an atomic, if a hill of atoms, you get to one final. But with molecular, it has 2 attached, and that's what gives it the behavior and why it is the way it is with the 2 that are attached. Molecular compounds are formed from 2 or more nonmetals. The basic unit for molecular compounds are molecules composed of constituent atoms. They just join together. Molecular compounds share electrons to make octets. So now we're going to try to go even more into understanding how and why compounds form. So we're looking at two nonmetals. If they form a pairing, what they're trying to do is form an octet around each atom. And they will do that by sharing electrons in order to fill that. So this Nm means nonmetal and this Nm means nonmetal. So in this case, this one has 2, 4, 6, 7. So this is a halogen. This is a halogen. That means that this element, this atom, has an open spot to take an electron. If it does, it has a filled octet like the noble gases all do, and it's very stable, and it will be left alone. Remember, chemistry is all about the lowest energy level, makes it stable. So these will join together, and when they join, they will share that lone electron and create a bond. And now if you count this, this has 2, 4, 6, 8 electrons. It's got an octet. And this has 2, 4, 6, 8. It has an octet. And this is a bond between those two. And we call that sharing of electrons a covalent bond. So when we talk about molecules coming together, this chlorine, this is a perfect example because this is a halogen and this is a halogen. So this is a perfect example of a chlorine and a chlorine. And when it comes together, it creates a bond between them. And so they're sharing 2 electrons between these both chlorine atoms here. Okay, so we've already discussed this. Let's go on. The basic units that compose dry ice, a molecular compound, are CO2. So these are also trying to create octets. Everything that is not hydrogen or helium is trying to create an octet around it to be as stable as possible. So that's why some metals will lose electrons in order to fill an octet, because when they lose those extra electrons, they take on the noble gas configuration, which has 8 around them. So that's why it's so easily for metals to lose some, because if they lose them, they will eventually get to an octet on the lower level of what that noble gas was. The basic unit that composes table salt is an ionic compound. It is a formula unit. So let me explain this here. When we're dealing with nonmetals and it's a compound, we call it molecules, molecular, because molecular indicates that you're dealing with nonmetals. When you're dealing with ionic compounds, which is a metal and a nonmetal, we call it formula units. Well, here's the thing. People get lazy in chemistry and they call everything molecules. Everything. So you need to know that an ionic compound is called formula units, formula mass. When you're dealing, anything with the word formula is dealing with an ionic. When you're dealing with molecules, it's nonmetal. However, in some things, as you start reading, people get lazy. You need to know the difference, even if you use those lazy terms as well. They are there for a reason. Okay, so ionic compounds. When a metal, which always wants to lose its electrons, combines with a nonmetal, it will, and the nonmetal wants to take electrons. That's where the word electron affinity, which we haven't really discussed, but that's what it means, is the love for electrons, has a tendency to gain these electrons. So when these electrons are transferred, it will fill in that empty hole or holes within that nonmetal, and that metal will lose that electron and take up the noble gas configuration that was prior to it. So a compound composed of a metal and a nonmetal is considered ionic. That's a transfer of electrons. There's charges that are holding this together. They call it electrostatic attraction. The basic unit of ionic compounds is the formula unit. Where's that word formula again? Ionic. Unlike molecular compounds, ionic compounds do not contain individual molecules, but rather cations and anions in alternating three-dimensional array. That's what we're talking about, that lattice structure here. So instead of just counting all of those millions and millions of atoms and dealing with scientific numbers, we simply look at what it's made and we leave it at that. So here's an example. This could be very well sodium chloride. Sodium will lose 1 electron. Chloride has an opening because it's got 7 valence electrons, but it can take 1 more. 1 more will get it to the noble gas configuration next to it. So this will lose that 1. Now it has an imbalance of more protons than electrons, which creates the positive charge. This now has an imbalance of more electrons than protons, which has a negative charge. That keeps that together. That is a very, very, very strong bonds. Ionic compounds have extremely strong bonds. Ionic compounds are solids in room temperature, and if you've ever tried to burn salt, it takes, I think it's 2300 degrees Celsius to burn it, It's really, so this gives you an idea of how strong these bonds are. This attractions of negative and positive, very, very strong. Okay, which image represents a molecular compound? So since I already just discussed ionic and how they are, you should immediately look at BA and go, nope, that's not it. Because that is an ionic. They are very organized. It is discrete patterns and of a solid, and they alternate. So it would be B. And remember the colors there. So that's hydrogen, and those are carbons, which you're not going to need to know on this one. But once you start learning the colors, that's going to allow you to see what that is. And then you could count those if you were asked to, and you could figure out what that is. So the figure represents a molecular compound. The answer is B, because it exists as individual molecules. That's the individual molecules. That's how we count them. And in those individual molecules, then we use the subscripts to determine how many atoms are in there. Figure A represents an ionic compound in a lattice structure. That's the term lattice structure is what we use. It's a crystal structure of very organized atoms in an organized pattern, and that's all based on the transfer of electrons of the positive and the negative charges. Okay, so we are now going to classify each substance as an atomic element, molecular element, or molecular compound, or ionic compound. So let's take a look at krypton. First, you need to know what krypton is and where it is in the periodic table. So you should know that krypton is a halogen. So it being krypton, it is a noble gas. Noble gases have filled 8 electrons around it. So it is not diatomic. So it is an atomic element. Sorry, here I got distracted. Okay, so first this is a nonmetal. It is a noble gas, and it's not diatomic. So it is an atomic element. Second one, this is cobalt-2 chloride. This has different compounds attached together. It has one cobalt, which is a metal, and it has 2 chlorine atoms, which are nonmetal. So this is a metal and a nonmetal. This is an ionic compound. This is very similar to this, but it's actually a little bit more complicated because it has 2 chlorines attached to the metal, or surrounding the metal is what I should say. Nitrogen. So again, where's nitrogen? Nitrogen is a nonmetal, and it's also a diatomic molecule because you're going to memorize and learn that 7 diatomic gases, diatomic molecules. So this is a molecular element. Okay, so we have sulfur dioxide. It has 2 nonmetals. So this is sulfur and oxygen, and they're both, it says it here, nonmetals. It is a molecular compound, fixed ratio. And the last one is potassium nitrate. We have a polyatomic ion, which is a nonmetal with a charge, and we have a metal. So this is 3 elements in it. A potassium, a metal, nitrogen, a nonmetal, and oxygen, another nonmetal. So 2 nonmetals and 1 metal. This is an ionic compound because there's a transfer of electrons from the metal to the polyatomic ion. And that's it.